In this exciting chapter, we will study transformations in the plane and the three-dimensional space by employing component spaces. Now, I don't have to tell you how important this topic is in applied mathematics, physics, engineering, architecture, computer graphics, you name it. And I'd like you to recall that we have already learned a great deal about these transformations without the use of component spaces. Well, you will see that component spaces will help us blow our earlier discoveries right out of the water. And let me also tell you why I think that this chapter is particularly exciting. Until now, we have been climbing the rather steep mountain of linear algebra, and many of our discussions would throw something at you that you were seeing for the very first time. Well, this chapter, with one exception of the new and very important concept of the dot product, is all about harvesting what we sowed. Having weathered the tempest of new ideas, we will now enjoy a very long run of smooth sailing, and we will begin to sow the seeds for the third and final pillar of linear algebra, the inner product. The entire discussion will take place with respect to Cartesian bases. Now, I hope that by now I have convinced you that one's choice of basis always requires careful justification. So I owe you an explanation for why we're going to use Cartesian bases. And there are two reasons for that. Number one, we won't be talking about any problem specific enough that it will dictate its own choice of basis. So we might as well use a basis that offers other conveniences, which a Cartesian basis certainly does. And the second reason is that while we won't be talking about anything particularly complicated, we will make a lot of new discoveries. So as far as presenting the material, this is a good case for going from the specific to the general. So we will make our discoveries with respect to Cartesian bases, and then we will immediately ask ourselves, what would the answer have looked like if the basis had not been Cartesian, if the basis had been arbitrary? So these two reasons make the Cartesian basis a good choice. And since we will use these kinds of bases throughout our discussion, these two diagrams, one illustrating a Cartesian basis in the plane, and the other one illustrating it in the three-dimensional space, will stay on the board throughout. And we will refer to these bases by the capital letter C for Cartesian. So, we will begin by talking about lengths and angles and their representations in the component space. And talking about lengths and angles will lead us to the very important discussion of the dot product, which is one of the most beautiful ideas in all of linear algebra. Then we'll talk about rigid transformations. What is a rigid transformation? Just think of a rigid body, like this beautiful sculpture by Gary Zayon. What do we mean when we say that a body is rigid? What we mean is that we cannot change its shape no matter what we do to it. In other words, the distances between any 2 points remain unchanged. So that's exactly what rigid transformations are. Rigid transformations are simply transformations that don't change the distances between any 2 points. And these include rotations, reflections, which is what you experience when you look in the mirror, and shifts. And having talked about lengths, we will be perfectly set up to talk about rigid transformations. And after we talk about these transformations which don't change any of the distances, we'll talk about another simple kinds of transformations that do nothing but change distances. In a very specific way though. They choose orthogonal directions, 2 in the plane or 3 in the three-dimensional space, and do nothing but stretch and shrink the body along those directions. Now these transformations are usually called symmetric for reasons that you will understand later. But I don't like the word symmetric because it has a very clear geometric connotation which is inconsistent with what symmetric transformations do. So we will call these transformations orthoscaling. Now that's a new term that I invented, and it is not a pretty word, so I don't think it'll stick. But at least it is very accurate in terms of describing what these transformations do. So that's our plan of attack. This chapter is full of highlights. So let me mention just 2 of them, and both of them have to do with the fact that even the most complicated transformations can be viewed in very simple ways. Here is highlight number 1. We will show rather easily that an arbitrary rotation is actually equivalent to a single simple rotation with respect to a stationary axis by some angle. So the only trick is to determine the stationary axis and the angle by which to rotate, and that captures all of rotations. This important and perhaps surprising fact has a very straightforward and equally important consequence, and that is any rigid transformation of a physical body, and I'm saying physical body to mean the things that we can actually do to a rigid body in our physical space. That excludes reflections. So any physical rigid transformation, no matter how complicated, is equivalent to a single rotation with respect to a stationary axis, followed by a single shift. That's all. That's how simple all rigid transformations are. Despite the apparent variety and the apparent complexity, they're that simple. So that was our first highlight that had to do with rigid transformations. Now let's talk about highlight number 2, which has to do with arbitrary linear transformations. And let's concentrate on the three-dimensional space and recall the fact that any 3x3 matrix corresponds to some linear transformation in the three-dimensional space. And there's great variety among 3x3 matrices, so there's great variety and of course complexity among linear transformations in the three-dimensional space. And if we were to look at it from the point of view of eigenanalysis, different scenarios are possible. There could be 3 eigenvalues and 3 corresponding eigenvectors, or the matrix could be defective, or there could be some mix of real and complex eigenvalues. And all of these properties actually tell us something about the linear transformation itself. For example, if we have 3 distinct eigenvectors, then all the transformation really does is stretch, shrink, and possibly flip the body according to those special eigendirections. So that's perhaps the best case scenario. Other transformations are more complicated to view simply. Well, we will show, and it's almost hard to believe that it's true, but it is, and it's actually not hard to show, that any linear transformation in space is equivalent to a combination of 2 transformations, a rotation followed by scaling according to 3 orthogonal directions, or the same kinds of transformations in the opposite order, stretching along or shrinking along orthogonal directions first, followed by a single rotation. So no matter how complicated the linear transformation is, it can be broken down into 2 simple and easy to understand steps. And of course, these geometric facts will be proven algebraically and also have analogs in higher dimensional arithmetic spaces Rn. So we'll talk about the geometric implications and we'll talk about the algebraic generalizations to higher dimensional spaces. And that part of the discussion will be pure algebra. So let's use this theorem as our symbolic goal for this chapter and slowly work towards it and enjoy the journey.